Today we're talking about the real world challenges that I am currently facing about retrieval augmented generation. Hi everyone, my name is Arthur and welcome to this presentation. First things first, let's start with some data. Do you know that the cost to train a 13 billion parameter model on 1.4 million tokens is about $1 million. So training a custom LLM for us, a large language model, it's not viable, and for most companies that is not viable at all. It is a real problem because most companies have private data that they want to talk with the LLM about their private data, but they cannot because the LLM was trained on a custom data set that doesn't contain the private data that the company wants to talk about. And that is a real problem. So how are we used to talk with LLMs? Usually we do a no-stop trip where we have a request and we have the LLM in the other side and we have our question. For example, what are the most aggressive dogs? We ask this question to the LLM and we hope the LLM can answer this question for us. And thankfully, the LLM will answer this question. That might work really well because that is a generic question that probably the LLM has already seen this. And the only context that the LLM will use is its training data. So that's why it might work really well, because aggressive dogs, training data sets probably contain this large training data sets. So, but what if we want to ask the LLM this question right here? Am I allowed to download external applications in my work machine? Spoiler, I cannot in my work. But because of security, of course. That won't work because we are asking a really specific question. Like, am I allowed to download external applications in my work machine? The LLM hasn't seen this because that is our private data. So the training data will not have this kind of information, as you see right here, and I am really sure that this won't happen. So what if we could go to our database and grab our private information before asking the LLM? That's where retrieval augmented generation comes in. So instead of making a no-stop trip, we are going to make just one stop. So before we go right into the LLM, we are going to make a stop at our database and somehow grab this information, the information that we want in the database. So we have a question. Am I allowed to download external applications in my work machine? We have our database, which contains this information. The database might have PDFs, SQL queries, CSVs, whatever, TXT files, plain text files, web pages, whatever. But it probably contains this information that we want. And somehow we grab this information inside the database and we use it as a context, a query improvement, enhancement to the LLM. So look at our final query. The primary query was, am I allowed to download external applications in my work machine? The enhanced query is, based on this information, answer. Am I allowed to download external applications in my work machine? And the information that we want is contained inside the database, and somehow we're going to grab it. And this is retrieval augmented generation, basically, in a really, really simple way of explaining. So this database right here, we have a special name for it. So introducing vector databases. What are vector databases? Before we start, let's start with some examples. We have Chroma, Quadrant, Weaviate, Pinecom, pgvector. This is not Postgres. It is Postgres, but it is a special database that they made just for storing vectors. Yes, it is a very profitable business. Vector databases. We have Milvus and many, many more. But what differs them from regular databases? Well, normal databases store entities, while vector databases store vectors, basically. But what are vectors essentially? What are those kind of vectors that I am talking about? So when we are talking about vectors in retrieval augmented generation, we are usually talking about embeddings. So you will see this word a lot when talking about retrieval augmented generation, RAG applications. And a embedding is nothing else than a number representation. You can think about it as a vector array representation of your text. So usually we have our text. In this case, I really like my dog. His name is Thor, and this is true. I have a dog named Thor. And we take this text and we pass it into our embedding model, which will transform this text into a number representation of it. But we are not limited to text. We can use audios. We can take the audio, convert to embeddings, and store those embeddings in our vector database. But we can also use images. We can take our image and somehow store in our vector database, which we will see later. But somehow this works. We can work with texts, audios, and images, and many more. So, just a fun fact, how many dimensions do you think a embedding can have? I talked about vectors, so you usually imagine vectors as a one-dimensional array, two-dimensional array, maybe three-dimensional array, but what about embeddings? Do you think they have, 2 dimensions? The maximum that they can have is 2 dimensions? Well, no. Maybe 3 dimensions, because it is a complex sentence may, I don't know, be represented in a 3D space, but no, the maximum is not 3D. So maybe 4 dimensions it can handle our case. Well, no, maybe 40 dimensions. Yeah, I think 40 dimensions is enough, but no. The maximum is 1024 dimensions. Just for you to see that sentences are complex, and searching inside our database about the sentences can be really tricky for us, and that's why vector databases are optimized for this kind of task. So usually, now we have a better diagram. We have still a one-stop trip, which we have a request with a question. We ask the vector database on a task called similarity search, which is really common. You will hear this word a lot. We take our question, we make some similarity search somehow in our database. We retrieve the most relevant documents, and these documents are used as context to the LLM. And the query is still the same, or kind of the same. Some implementations make the query a little bit different, like they add a text at the end of the query, like you are only allowed to answer about the documents you have received. If you don't know the answer, just say no. But the query may vary, okay? But essentially what happens is this. We have our documents, we have our query with the context and the question we asked, and now we will ask the LLM. And as you can see, the training data will not have this kind of information, but the context will help the LLM answer our question. It's almost like you take a piece of text and give it to GPT. You know, you take a text that you want to make a summary about it. I don't know. And you copy and paste to the GPT model. And after you copy and paste, you make a question like, explain me about this, whatever. And GPT will now know that you are talking about this piece of data. And that's what we are doing right here. What we are using context. We're giving context to the LLM. Okay. But unfortunately, it's not that simple. It is not really that simple. Here is a diagram that I took from NVIDIA, and the workflow looks like this. So we need to talk to our documents, essentially. So we need somehow to ingest those documents inside our vector database, of course. We have to ingest these documents. So you can look at the left right here that we have our database. We want to be able to ingest those documents inside our database. And after a while, we want to retrieve the information from those documents. But first, these documents have to be converted to embeddings. So we want to have a embedding model between the documents and the document database, the vector database. We will convert somehow these documents to text, and this text will be converted to embeddings, and the embeddings are going to be stored on the vector database. The same goes from images, audios, etc. So the vector database is not a problem. We have many of them, but the framework is kind of hard. We have nowadays we have LangChain and Llama Index. I am currently using LangChain because it is more famous, but Llama Index is really good for this kind of task, RAG, Retrieval Augmented Generation. But the framework you're going to choose, it actually doesn't matter. The result should be good, no matter the framework you choose. So you can see in this diagram that we have an embedding model. We retrieve those documents from our document database. We pass it into our embedding model, and we store it inside our vector database. But hey, the LLM doesn't understand plain text, so the query the user makes is also going to be converted to embeddings. So we gotta convert embeddings, text to embeddings, the document text to embeddings. We have to convert the user query to embeddings in order to perform a similarity search in our database. And let me see if I am missing something. I don't think so. Maybe I am, but it is a complex task. But usually you will make this kind of flow. If the user is asking a question, you will convert this question to embeddings. You will perform a similarity search in your vector database. The vector database is going to return the most similar documents, maybe with some page information or some metadata. And you're going to use this metadata to to give it as a context to the LLM. And usually the framework will do this for you. For example, LangChain, we have retrievers, which we can convert our database, our vector databases, to retrievers. We can say like this. And those retrievers will do the hard work for you. Will retrieve the most relevant documents. You'll usually give them the query, and it will use it as context to the LLM. So you saw that this is not an easy question. beside the fact that if you look in the documentation of those frameworks, usually the example they give is not actually, it's not viable for production, because they give examples with like 4 lines of code, because Python is really known because it is really easy to make things. You can do many things with just 1 line of code, and that's not possible with this kind of task. Really not possible. So the examples they give you are just for one-time usage. Let's say like this, where you have your documents. I want to now and only now talk with them, and after I close my application, the documents are gone. If I open the application again, if I open the server again, I will have to convert those documents to embeddings, store them in a in-memory database, vector database, make some queries about them, and that's not viable for production. That is not viable for production, especially if you want to ingest documents at real time. You know, the application is already running, and hey, let's suppose that I am working in a university and I want to store some books in my vector database. And I did this when the application started, but somehow I forgot to add a book. Will I have to turn all of my application down in order to add the extra document? That is not viable for production, and that's why we should be able to ingest documents at real time, anytime we want. And it's a problem. It's not a problem, it is a challenge. It is possible, many people have done it, but it takes some time for you to properly organize things. So what are the challenges that we can face on retrieval augmented generation and you should be aware of? First, documents can be any type, and this introduces various complexities because it can lead to scalability problems if not done well. For example, I might have to ingest SQL documents, PDFs, plain text, CSVs, and I would constantly have to ingest and retrieve. Usually, I would take care of ingestion, because once it is inside my vector database, I would not care if it was a SQL query or a PDF, but ingestion itself is really hard because documents can be unstructured, and this is a problem. This is a problem because let's take PDFs can be unstructured. You know, it can have tables, complex tables. It can have one section right here and one section right here that is related to this section. But when you ingest those documents, you usually take these documents and get chunks of it. You usually don't store the whole document inside the vector database. You kind of split it in many chunks, but it is still the same document, but it is many chunks, and you store those chunks in vector database because it is more optimal for searching and also storing. You wouldn't store a whole document inside your vector database. This is a problem. PDFs are really a nightmare, and we are still trying to figure it out how to do PDF ingestion well. Well, at least I am in my company. I am doing this kind of job, and I have heard about some APIs and some libraries. I'm currently using Unstructured to ingest those PDFs, but I am still experimenting a lot of tools because making toy software is really easy. Making toy software, anyone can make toy software, and As I said, this can be done in 4 lines of code. But if you think of the problems on doing this with 4 lines of code, there are many problems, especially in real production environments. So extracting information about these PDFs are really hard. And hey, I forgot to mention websites, web pages. Did I forget to mention something? Will I have to worry about anything else? Any kind of document? Well, what I thought based on this complexity is this should be a data ingestion microservice. Because it is really complex. I have to handle many types of documents. And hey, this should be a microservice in my opinion. I may be wrong. If I am wrong, you can just, hey, help me. Just type a comment. Let's chat about this and anything. So this should be a data ingestion microservice. But actually vector databases operations are also really hard, and I think they should be contained on their own microservice as well. So now we have 2 microservices. Am I forgetting something? Well, of course I am. I'm forgetting about the language models, the LLMs. So LLM inferences can lead to concurrency problems. So imagine I have 2 persons using the same language model, and will the second one have to wait the first to stop talking with the large language model in order to talk to it? That is another problem that can be solved and will be solved. Today I'm here to talk about the challenges that you may face in a real software, not a toy software. So real softwares and real solutions might have this kind of problem where you want to be able to receive many requests to the LLM and be able to properly handle those requests. So the workflow would look something like this. We have the request, we use some API, and the API will inference properly the large language model. So this can lead to concurrency problems, as I said, and hopefully, thank God, we have a solution for this, which in this case is Ollama. Ollama is a microservice. It's a Docker container, whatever you can call it. It is a containerized environment, application, whatever, where you can make inferences through an API to the LLM of your choice. So you usually just do like Ollama pull Llama 2, for example, and the Llama 2 model can now be used as inference in the API. And Ollama can handle those kind of requests properly, and it will handle, so we don't have to reinvent the wheel. Okay, so now we have 3 microservices, and number 4, it should be hardware efficient. In my case, actually in many cases, because hardware efficiency is really important. We don't want to waste resources. We don't want to make useless inferences to the LLMs. We want to be able to cache the embeddings. If the embeddings repeat a lot, we would have a cache system to store properly those embeddings. And in my case, it should be low cost. Actually, in my case, it should be free. It should be free. And this is a real problem. So making a thing like this, a software like this, without investing any kind of money, it is possible, of course, but it can lead to hardware problems because LLMs are really hardware expensive and hardware consumers. And making optimized inferences to the LLMs and getting streamed responses can be really tricky. But it is possible because we have, for example, Llama CPP that helps you run, for example, Llama models on a CPU efficiently. It is kind of a door between the LLM model and your inferences. It is made on C and C++. Really, you should take a look on their project. And as I said, that ain't easy to solve. And I have planned to write some code in this presentation, but I think I will do this in another video, a dedicated video. This is the problematic video. In this video, I introduced some challenges, but those challenges can be solved. And I will show you some examples on how you can solve this kind of challenges in the next video, because I had some experience with it and I am currently having a lot of experiences with retrieval augmented generation, and I'm going to tell you it is possible and you can do it. All right, if you're doing an application like this, you can do it and you will do it. Okay, because it is not impossible. It is possible, and I trust on you. You can do this, okay? And we're doing it together. And that's it. My name is Arthur. If you want to follow me on any social media, my LinkedIn is in the description. I don't know, in the below, above. I don't know where is it, but it is somewhere. My social medias. And that's it. I hope you enjoyed it, and see you in the next video. Goodbye.